What if not only is the universe expanding, but also Earth? And what if the crazy hypothesis that our planet is growing, literally inflating like a balloon, is actually not so crazy after all? We've all heard about the flat Earth theory a million times. Despite how absurd it is, there are still people who believe in it. There are slightly less popular but no less, let's say, extreme ideas, such as the hollow Earth theory, or even the idea that Earth might have some kind of cellular structure. But a growing or expanding Earth is not just a conspiracy theory from the depths of the internet, although some conspiracy theorists do of course love this idea. But the difference here is that the expanding Earth hypothesis was seriously considered by scientists and was once a part of the scientific mainstream. Of course, there was a time when everyone thought that the Earth was flat, but that was hundreds or even thousands of years ago. However, your grandparents, parents, and maybe even some of you could have been alive when the expanding Earth hypothesis was a more or less accepted scientific theory. This was during the first half of the 20th century. What is also interesting in this story is that even after the expanding Earth hypothesis ceased to be dominant, there were still quite a few scientists who supported it for a long time. Even some papers on that topic were still being published even after I myself had been born. Today this idea has mostly moved into the realm of pseudoscience, but that doesn't stop it from still finding supporters, primarily among enthusiasts of conspiracy theories. They're like, oh, scientists rejected this idea. Give it to us. But really, this story is very interesting. Where did the idea that the Earth might be expanding come from? How did it become mainstream and how did it transition into pseudoscience? What were the advantages and problems of the hypothesis and how could the Earth physically expand? And what would the mechanism of planetary growth be? Let's talk about all this today. I'm Andrei, and this is Cosmos Elementary. In fact, the idea can be expanded a bit, no pun intended. Alongside the expanding Earth hypothesis, there was also discussions about the idea of a contracting or shrinking Earth, as well as the concept of a pulsating Earth that cyclically expands and contracts. Overall, the idea that a celestial body, and Earth in particular, can change its size is not so crazy. Clearly, over billions of years of planetary evolution, Earth couldn't have remained the same size since its formation. First of all, during the formation stage, proto-Earth actively grew in size by accumulating mass from the protoplanetary disk and through collisions with other bodies. And even now, Earth constantly receives material from space, which can increase its mass. We will discuss this in more detail later. As for the shrinking of planets or moons, that's also quite a plausible scenario. Take our moon, for example. There is evidence suggesting that it has been shrinking in relatively recent history, and it may even be shrinking now. Evidence for this includes features on the lunar surface, such as cracks and displacements in the lunar crust. These can form because the moon is cooling down. It's no secret that when a substance is heated, it expands, and when it cools, it contracts. If you put an inflated balloon in the cold, it will shrink in size, and in high temperatures, it will expand. But the moon is not elastic like a balloon. Instead, as it cools down, it tends to crack. And there's nothing surprising about it cooling down either. The heat generated by the decay of radioactive elements in the moon's interior is not infinite, nor is the heat remaining from the early stages of the moon's evolution, since its formation and the period when it was heated by collisions with other bodies. If such cracks, faults and displacements were found only in a specific region, it might be due to some local process. However, images from the LRO spacecraft, which takes high-resolution images of the entire moon, show these features across the lunar surface. This suggests that the process is likely global, and a good explanation for this is the moon's cooling and reduction in size. Based on measurements of these surface features, estimates suggest that the moon's radius has decreased by at least 100 meters, or about 330 feet. And studies from 2019 suggest that this process may still be ongoing. Another well-known example is Mercury. There, similar features to those on the moon have been found, but they are even larger, taller and longer. The formation of these features is also explained by the cooling of the planet's interior and the reduction in size. Previous estimates suggested that the planet's radius could have decreased by as much as 7 kilometers or 4.3 miles, but more recent estimates are more conservative, indicating a reduction in size of about 2 kilometers or 1.2 miles. Overall, the idea that an entire planet can change size is not that crazy. It is a far cry from the flat Earth theory. Although, even in the scientific theory of the expanding Earth, there was at the time its own share of nonsense. So, how did anyone come up with the idea that the Earth should be expanding? Even before the advent of modern theories, people looked at world maps and coastlines of continents and noticed something peculiar. For example, if you look at the western coast of Africa, it seems that the coastline resembles the eastern coast of South America, and this is also true for other continents. It seems as though the shapes of the continents are not random and they fit together like puzzle pieces. In fact, the resemblance appears even more pronounced when looking not just at the coastlines, but at the underwater continental shelves. Today, any student who pays at least some attention in their geography class, or someone who remembers something from their school curriculum, or a person who has an interest in this topic, knows that it works something like this. The plates that make up the lithosphere are not static. They're mobile and can move. What we observe today as separate continents once was a single supercontinent called Pangaea, which began to break apart around 200 million years ago. There is a wealth of evidence supporting this explanation, but it's interesting to note that this theory only became widely accepted relatively recently, even though hints of it had appeared hundreds of years earlier. In some popular articles on this topic, especially older ones, you might find the claim that the first person to notice the similarity between the coastlines of Africa and South America was the famous English philosopher Francis Bacon. And he did this as early as 1620 in his book Novum Organum. He wrote that the similarity could not be a coincidence, and people have concluded that he was the first to stumble upon the idea that these continents were once joined together. But actually, it's not quite like that. The full text of this book is available online, and I'll leave a link to it in the description. In reality, Bacon doesn't explicitly state that the west coast of Africa fits the east coast of America. Rather, he notes the general similarity of the continents. And again, he didn't explicitly suggest that they fit together like fragments of something that was once whole. Moreover, he does not discuss the mechanism or movement of the continents. However, it is possible that even earlier, the cartographer and author of the first geographical atlas, Abraham Ortelius, noticed this. Here is a world map from his 1570 atlas. And here is a version from the 1598 edition. He not only noticed the similarity of the coastlines, but also suggested the movement of land masses as a possible explanation. He believed that a catastrophic event, such as a flood that supposedly sank Atlantis, could be responsible. In the following centuries, several other people also noted the similarity of continents' coastlines. For example, here is a drawing by the French geographer Antonio Snyder Pellegrini from 1858. He explained it by the biblical flood, though it's unclear how he thought it would have caused the continents to shift. The first scientific theory of continental drift was proposed by Alfred Wegener in 1912. He proposed that all the present continents were once part of a single supercontinent, which he called Pangaea. Here is the original paper. In addition to the visual similarity of coastlines, which had been noted long before him, he presented other arguments. For example, both South America and Africa had fossil remnants of the same plants and animals from the same time period. Similar findings were observed on other continents as well, and many of these organisms could not have crossed the oceans. At that time, there was a theory that land bridges might have connected all the continents. However, the idea that the continents were once a single whole seemed more likely, further supporting the idea that separate land masses were once a single supercontinent were the marks left by glaciers during the ice ages. Wegener also proposed that continental drift was a mechanism for the formation of mountains. Despite all of this, Wegener's theory was not taken seriously at the time, primarily due to the lack of an explanation for the mechanism of continental drift. Wegener had ideas, but none of them were supported by calculations. Therefore, in the first half of the 20th century, the leading explanation for this was the expanding Earth hypothesis. According to this idea, continents drift apart because the Earth is literally increasing in size. Until the 20th century, scientists had very limited experimental methods to test a particular scientific theory, or none at all, so they had to speculate. By the beginning of 20th century, the dominant model was the geodynamic model of contracting Earth. However, new discoveries and research weakened that theory. For example, when it was discovered that the decay of radioactive elements heats the Earth's interior, it was calculated that due to this heating, the Earth could not cool down quickly enough to account for the observed tectonic features through the contraction of the planet. Additionally, the development of radiometric dating helped determine when significant geological events occurred, and once again, this did not align with the contracting Earth hypothesis. And that's not all. The main point is that the problems with contraction hypothesis led scientists to consider alternatives. Among the alternatives were Earth's expansion, Earth's pulsation, and continental drift, which most people did not take seriously at the time. The expanding Earth hypothesis also had a relatively long history, and was already known as early as the 19th century. One of the main arguments in favor of the expanding Earth hypothesis against continental drift was the claim that on smaller Earth, the edges of the continents fit together better. Conversely, if you simply move the continents closer together on an unchanged Earth, gaps remain between them. This hypothesis was tested not just with drawings, but with three-dimensional models. They made physical globes of different sizes by hand and examined how the continents fit together on them. Even without modern experimental data, the expanding Earth hypothesis has several issues. For example, the main argument is that the coastlines of continents fit together. But if the Earth is somehow increasing in size, the Earth's lithosphere would need to adjust accordingly. Beyond just increasing the distance between continents, the continents themselves would likely also deform. If you take a ball, cover it with pieces of clay, and then inflate the ball to make it larger, the clay will most likely deform, crack, and break, rather than just expand proportionally while maintaining their original contours and continuing to fit together like pieces of a puzzle. If the Earth were truly expanding, we would observe certain global features in the crust. Faults and cracks in specific patterns similar to cracks in dried soil would be expected. However, we do not see that. Before we continue further, let's briefly review the current theory. The prevailing theory today is called plate tectonics, not continental drift, which was proposed by Wegener. Plate tectonics was developed later. The main difference is that unlike continental drift, plate tectonics provides a mechanism that explains the movement of segments of the Earth's surface. According to the modern theory, the lithosphere, the outer solid shell of our planet that includes the crust and the upper layer of the mantle, is not a continuous layer, but consists of separate lithospheric or tectonic plates. There are 7 major plates on which the continents are located, along with several smaller plates. These plates move very slowly but continuously. This movement is likely due to the asthenosphere, a layer in the upper mantle, being more plastic than the surrounding layers. Sometimes the asthenosphere is compared to a lubricant on which the plates slide. But the main force driving plate movement is mantle convection. The mantle is mostly composed of solid rock. If we dug out a piece from the mantle, it would essentially look like a rock. However, it is still subject to convection. Inside the Earth, a similar process occurs as in a pot of boiling water, where water heats up from below, rises to the top, cools down, and then the cooled water sinks back down, repeating the cycle. Only instead of water, it's mantle rock that heats up in the depths from the Earth's core. Warmer mantle rock rises towards the crust, cools down, and then sinks back down. This process occurs very slowly, with one cycle of tens of millions of years. So primarily, convection drives the movement of the plates, although there are other factors involved. There are several scenarios for what can happen where two plates meet. If plates move towards each other, the boundary may feature a subduction zone, where one plate is forced beneath another. If the plates move in the opposite directions, we observe a spreading zone. Plates can also move parallel to each other, but at different speeds. These boundaries are called transform boundaries. In spreading zones located on the ocean floor at plate boundaries, melted rock rises to the surface and cools, forming a new young oceanic crust. In subduction zones, old crust is pushed down into the mantle. The processes I described have been experimentally and observationally confirmed, and this is why the theory of plate tectonics is considered widely accepted today. For instance, thanks to detailed mapping of the seafloor, along with advancements in seismographic and magnetic research. Seismographs, which have been increasingly deployed worldwide, revealed that earthquake epicenters are not randomly distributed but are located in specific areas along the boundaries of lithospheric plates. Active volcanism is also observed in these regions. In spreading zones, mid-ocean ridges are found. These are mountain systems that form where new hot rock emerges at the surface. When ships were equipped with magnetometers in the mid-20th century and began exploring the seafloor, they discovered something unusual: so-called magnetic stripe anomalies. Along the ridges, parallel to them on both sides, symmetrical bands of rock with alternating magnetic polarities spread out. This creates a kind of a magnetic zebra-like pattern. A ridge, then stripes of normal polarity on either side, followed symmetrically by two stripes of reversed polarity, and so on. This anomaly is explained as follows. Basalt, which makes up a significant portion of the oceanic crust, can be magnetized relatively easily. And when the hot rock cools, it retains the magnetic properties and the orientation of the Earth's magnetic field at that time. But, as we know today, the Earth's magnetic field undergoes reversals from time to time, meaning the magnetic poles switch places. This occurs relatively randomly over time, but on average every few 100,000 years. While the direction of the magnetic field is one way, new rock emerges and solidifies in different directions in the spreading zone. Then, when a magnetic field reversal occurs, new rock continues to emerge, but records the new direction of the magnetic field. This process repeats with further reversals, creating parallel and symmetrical bands with different polarities. Dating the age of the crust also supports plate tectonics. The mechanisms of subduction and spreading also explain disappearance of old crust in some areas and the presence of a very young crust in others. These and other data solidified the position of plate tectonics theory, providing what was missing from Wegener's theory: a mechanism and evidence supporting that mechanism. But here's an interesting part. Proponents of the expanding Earth initially tried to use some of these data to their advantage, while with less than stellar results. Take, for example, the discovery of seafloor spreading. The formation of new crust and magnetic stripes could be interpreted as if the ocean floor is expanding, and therefore the Earth itself is growing. Data on the seafloor can be converted into expansion rate, and it turns out that if spreading were indeed a result of the Earth's own growth, then during the early Jurassic period, the Earth's diameter would have been 6,600 kilometers. This means that since then the Earth would have increased in size by a factor of 2. If we linearly extrapolate such a growth rate back in time, continuing to reduce the Earth at the same rate, it would imply that somewhere in Paleozoic around the Devonian period, the Earth would disappear. And we definitely know that the Earth is more than 400 million years old. Although, of course, there will be those who will argue about that as well. Then, proponents of expansion decided to abandon linear expansion and concluded that the Earth must be expanding exponentially. There are certainly questions about the basic physical properties of an expanding Earth. If it is indeed expanding, what is the source of this growth? If its mass is increasing, where does this additional mass come from? I mentioned earlier the most realistic scenario, which is accretion of material from space. During the formation phase, Earth did grow by accumulating material from the protoplanetary disk and through collisions with other bodies. However, this phase has long since ended. The Sun blew away the protoplanetary disk, and the period of frequent and large collisions ended. Such growth as occurred in the early solar system is no longer possible. And according to the expanding Earth hypothesis, it should have noticeably increased in size over the last several 100 million years. Currently, material continues to fall to Earth, with larger bodies occasionally reaching the surface becoming meteorites, but more commonly, it is cosmic dust that burns up in the atmosphere. While we cannot measure the exact amount of material that falls to Earth down to the gram, we can make some estimates. According to NASA, Earth receives about 48.5 tons of material per day, which amounts to approximately 18,000 tons per year. The mass of Earth is approximately 6 times 10 to the power of 24 kilograms, or 6,000 billion tons. Compared to this immense mass, the annual influx of 18,000 tons of space matter is minuscule. NASA even conducted some studies to check if Earth's radius changes significantly. Unlike early 20th century scientists, who had mostly to speculate here, NASA researchers have access to a wide range of modern measurement techniques. Laser measurements, GPS, very long baseline interferometry, and satellites measuring Earth's gravitational field, such as GRACE and GRACE-4 satellites. So, scientists concluded that the Earth at best increases by 0.1 millimeters per year, which is comparable to the thickness of a human hair. This result was considered statistically insignificant. The actual scientific paper stated, the solid Earth is not expanding within the measurement accuracy of 0.2 millimeters per year. In summary, both the theory of plate tectonics and modern measurements contradict the expanding Earth hypothesis. There is no realistic explanation for the level of planetary growth proposed by proponents of the idea. But there are also alternative hypotheses. Well, very alternative. What if new material is just being generated inside the Earth? Wait, what? It seems to a little contradict, well, fundamental laws of physics. However, there were hypotheses where similar ideas were discussed, such as in theories of a steady-state universe, which opposed the now widely accepted expanding universe theory. In those theories, it was proposed that new matter is constantly being created in the universe. However, no evidence has been found to support this. Even if we assume that matter were somehow being created inside the Earth, there would be numerous problems with this idea. Matter cannot spontaneously appear as atoms. It would have to emerge as particles such as neutrons. For these particles to form atoms, high temperatures and pressures are required, conditions that do not exist within the Earth. Moreover, free neutrons do not live long. They decay in about 15 minutes into protons, electrons, and antineutrinos. We should be able to detect this additional flow of antineutrinos, but we haven't. If there is no source for new mass, then perhaps the mass remains the same, but the volume changes. Then the average density of the planet should also change, which is another problem. Changes in mass, radius, and density lead to very significant changes in conditions. For example, if the planet's radius were twice as small, but with the same density as modern Earth, the surface gravity would be much weaker. The atmosphere would be much thinner and weaker, similar to that of Mars. And liquid water could not exist on the surface. We know that liquid water has been present for billions of years, and without it, life could not have developed. A smaller Earth with different properties might not have been able to retain its atmosphere at all. And the last massive Earth wouldn't have been able to retain the Moon, but the Moon still seems to be with us. A denser, smaller radius planet could have stronger surface gravity, which would also affect the evolution of living organisms, and not only that. And all the key events over billions of years of our planet, such as origin and evolution of life, the formation of oceans, require physical conditions close to the modern ones. In general, no matter how you look at it, making an expanding Earth realistic is challenging. As more data became available, the idea became increasingly closer to pseudoscience. However, it still had its supporters throughout the 20th century. In the Soviet Union, geologist Vladimir Larin proposed the so-called hypothesis of an initially hydride Earth, which was also supposed to expand. However, today this hypothesis is not taken seriously. Conspiracy theories generally use the same arguments about the coastlines of continents. They also present an argument like the following. If all modern continents were once a part of a single supercontinent, why was all of the land concentrated in one part of the Earth, leaving only the oceans on the other side? What is the likelihood of such a scenario? To answer this, it is important to note that Pangaea is actually a relatively recent development in Earth's geological history. And Pangaea was not the only supercontinent in the history of our planet. There have been others before it. Continents have fragmented into separate landmasses and then reassembled into supercontinents in cycles throughout geological time. On YouTube, you can find cool animations showing how the appearance of Earth's land masses has changed over billions of years. This story is a great example of how science can be conservative and how it can take decades for a theory to become widely accepted. Scientific progress often involves rigorous scrutiny and incremental validation, and even well-supported ideas can face resistance before gaining broad acceptance. But at the same time, when new data that are hard to dispute emerge, the consensus within the scientific community can change. No matter how reasonable and logical your theory might seem, without evidence, mechanisms, experimental data, or good models, no one will take it seriously. Unless there are absolutely no alternatives, and it is the best option available at the moment. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye!